Hello, ladies and gentlemen. My name is Simon Schmidt and I'm head of the Department of Hygrothermics at the Fraunhofer Institute for Building Physics, IBP. In this video about heat and moisture transfer, we will have a deeper look into the heat transfer. You may remember that in module 1.2 we already learned the basics of the U value, the parameter for assessing the heat flow between the outside and the inside of the wall. We will now take a closer look at this U value and you will learn how to calculate it. We will do this using our construction in LUCKNOW as an example where a stay-in-place formwork system is used. The second part of the video will be more about moisture again, and we will go through with each other how can we assess when moisture in the room becomes a problem. Now let's start with the heat transfer. We remember this slide from module 1.2, so we won't repeat it in great detail. If necessary, please go through the video or the corresponding transcript in advance to recall the information. Briefly summarized, the U value indicates the heat flow through a building component depending on the temperature gradient between the warm and the cold side in the unit watt per square meter and Kelvin. The unit describes the energy flow through the square meter in Kelvin. The U value can therefore be used to read off the insulation properties of a building component. The smaller the U value, the lower the heat dissipation through the component. So how can we calculate the U value and what input quantities do we need? Let's take a look at a simple design with a two-layered structure. The values on the right are already given to us by the construction. D1 and D2 indicate the thickness of the individual component in the construction. Lambda 1 and lambda 2 are the corresponding thermal conductivities of the respective components. Thermal conductivity data are usually provided directly by the building material manufacturers. RSE and RSE indicate the heat transfer resistance of the indoor air SE and outdoor air SE adjacent to the building component. These are usually fixed and can always be specified with the values given here. Next, we need the equation for calculating the U value. You can see this here. If we now enter the data from the right side here, we get a U value of 0.10 watt per square meter and Kelvin. In LUCKNOW, we have a stay-in-place formwork system. Here you can see the formwork. Normal concrete was used there. However, we will also take a look at U values of a comparable wall made of lightweight concrete. Here you can see the necessary material data. On the right, the standard concrete as used in LUCKNOW. On the left, the comparison, the alternative with lightweight concrete. The thicknesses are the same in both cases. We neglect the PVC webs here and do not include them in the calculation. The data above, inserted into the previously formula, results in the following U values. For the construction with the heavy concrete, the U value is 3.62 watt per square meter Kelvin. a relative high value. In contrast, the lightweight concrete construction has it much lower, with a U value of 0.95 watt per square meter in Kelvin. Since a high value means that a lot of heat flows through the wall unintentionally, a high value should be viewed negatively. From an energy efficiency point of view, it would therefore make sense to use a lightweight concrete construction instead. Of course, it must be ensured that it's also statically possible. So much again for the heat transport. Now we focus again on the moisture. If surfaces in a room are permanently too damp, this can lead to hygienic problems such as mold growth. But why does it happen that surfaces become damp in the first place? Basically, it is due to the same effect on the wall as on a cold beverage glass, where water condenses from the air on the outside on the cold surface and precipitates into drops. When the temperature changes, the storage capacity of the air changes in relative to the water. The colder the air becomes, the less water it can store at the same relative humidity. Let's look at an example. If we consider a cubic meter of air at 80% relative humidity at 30 degrees Celsius, it contains about 24 grams of water. If this air is now cooled down to 15 degrees dew point to participate, because at 15 degrees can contain a maximum of 13 grams of water. The difference condenses. With this method, we can now check how cold a surface may become on the outside and how could it may become on the inside before condensation starts to form. You can see the conditions from the climate inside and outside here at the bottom right. When a U value of 0.95 watt per square meter in Kelvin, the surface temperature on the inside of the wall results in 20 degrees Celsius and the surface humidity in 44%. At the outside surface it results in 30.4 degrees and 82.2 relative humidity at the surface. We now proceed with these values. Let's start with the interior. The air at 20 degrees Celsius contains about 7 grams of water. If we now go backwards and see that about 6 degrees surface temperature, the maximum capacity of the air is reached, and at lower temperatures water precipitates and mold problems can occur. We proceed in the same way for the outer surface, with a little over 25 grams of water contained. Dew water already precipitates for 27 degrees. Now we want to check how the relative humidity in the room behaves when the air is in contact with the wall surface that has a different temperature than the air temperature in the room. In this case, our air temperature in the room of 18 degrees is lower than the surface temperature of 20 degrees, because heat from outside comes through the wall to the inside and heats it up. This means that the relative humidity drops from 50% to 44% when it touches the wall. Now we calculate the same again, but assume that we ventilate via an open window. Thus the warm, moist air flows from the outside to the inside and comes into contact with the inside of the wall. In this case, only 18 degrees prevail in the room due to the active cooling. The relative humidity drops here from 80% to theoretical 190%. Of course, this is not possible. Instead, When the 100% is reached, condensation water escapes. This means that in this room that are cooled with AC, there should be no window ventilation, otherwise condensation will occur. Let us end this unit with a brief summary of the main findings. For the calculation of the U value, we need the thickness and the thermal conductivity. The calculation of the condensation depends on relative humidity and temperature differences. We could show that in the air condensed room we must not use window ventilation. Thank you for your attention and see you next time.